Tonight we are going to talk about something most people have never thought about. Not the danger of deep space, not the cold, the vacuum, the distance. You already know those things exist. What most people do not know is that the solar system itself is a shield. A physical structure maintained by the Sun that has been protecting everything inside it for 4.5 billion years. And most people have never noticed it. The way you do not notice the air in a room until someone opens a door to the outside. Leaving the solar system means leaving the shield, and the environment on the other side is not just deeper space. It is qualitatively different space. Space where certain dangers do not get bigger. They change kind. Space where the intuitive solution, add more shielding, build a better spacecraft, partially makes things worse rather than better. By the end of tonight, you will understand why leaving the solar system is not an engineering challenge that advanced technology will eventually solve. You will understand what the specific shape of the danger actually is. And you will understand why we know all of this, because a small machine crossed the boundary in 2012 and its instruments told us exactly what changed. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Imagine you have lived your entire life inside a building. Not a small building, a vast one, large enough to contain planets, comets, and everything you have ever known. The building has walls you cannot see and did not know were there. The air inside feels normal because it is the only air you have ever breathed. The light levels feel ordinary because they are the only light levels you have ever experienced. You have no reference point for what exists outside, because nothing you have ever encountered came from outside. Now imagine that for the first time in the history of the building, something small and mechanical crosses through the walls and sends back a reading. The reading says, it is different out there. Measurably, sharply, immediately different, not gradually different as you move toward the edge. Different at the line. That is in broad terms what happened in August of 2012. Voyager 1 had been traveling for 35 years. It launched in 1977, used the gravitational pull of Jupiter and Saturn to accelerate outward, and had been moving steadily away from the Sun ever since, at roughly 61,000 kilometers per hour. By 2012, it was approximately 121 astronomical units from the Sun. 121 times the distance between the Earth and the Sun, roughly 11 billion miles from home. On the spacecraft, one of the instruments still operating was the cosmic ray subsystem. It had been measuring the rate of energetic particles hitting its detector since launch. For most of the mission, those readings had been relatively stable. Inside the heliosphere, inside the Sun's protective magnetic bubble, the galactic cosmic ray environment was partially suppressed. The Sun's influence was doing something to the radiation environment, even at that extreme distance, even that far from the star itself. Then the readings changed. Not gradually, not over months of slow drift. In August of 2012, the cosmic ray count jumped sharply at a specific moment. The solar origin particles the instrument had been measuring dropped. The galactic origin particles increased. The transition was not a slope. It was a step. Before and after, with a kink between them that the team spent months analyzing before they were comfortable enough to say publicly, Voyager 1 has crossed the heliopause. 6 years later, Voyager 2 crossed the same boundary from a different angle. Same pattern. Step function. Inside. Suppressed. Outside. Elevated. The boundary is consistent. It surrounds the solar system. It is a real physical thing with a measurable location, and crossing it means entering a different radiation environment immediately and permanently. What those numbers mean is simple on the surface. The heliosphere reduces galactic cosmic ray intensity by approximately 75 to 90% compared to outside. What Voyager measured after crossing was not a modest increase. It was the full galactic environment, the radiation background that life on Earth has never directly experienced, because life evolved inside the shield and stayed there. Voyager 1 is a machine. It does not have biology to protect. It can absorb the radiation that changed at the heliopause in ways that tissue cannot. The instruments measured the change. They were not harmed by it in the way a crew would be. So the first question the data raises is simple. What would those numbers mean for a human being? Answering that requires understanding what the heliosphere actually is. There is something worth pausing on in the way that data arrived. The cosmic ray subsystem on Voyager 1 had been running for 35 years by the time the crossing happened. It had been sending readings continuously since 1977. Through the planetary flybys, through the long quiet transit, across the outer solar system, through the termination shock crossing in 2004, where the solar wind first began to slow. For 3.5 decades, the instrument had been doing its job in the background, producing data that was read and archived and analyzed by a rotating team of scientists at JPL who had dedicated significant portions of their careers to a mission that launched before many of them were born. The heliopause crossing was not a surprise in the sense of being unexpected. Scientists had predicted the heliosphere's outer boundary for decades. Theoretical models had estimated its location. The uncertainty was in the exact distance, the exact shape, the exact character of the boundary. What the models predicted was that at some point, Voyager would cross from the heliosphere into interstellar space, and that the crossing would be detectable in the particle data. What was somewhat surprising was the sharpness of the transition. The models had suggested the boundary might be gradual, a broad transition zone rather than a sharp line. The data showed it was sharp. The step function in the cosmic ray reading was not a weeks-long gradual change. It was a relatively abrupt shift at a specific moment. The heliosphere ends more like a wall in a fog, not a perfectly sharp wall. There is a boundary layer, a region of transition, but the change in radiation environment at the heliopause is far more abrupt than many scientists expected before the actual measurement. This matters for any mission that intends to cross the boundary deliberately. There is no gradual transition into the harsher environment. There is the shield, and then there is the absence of the shield. The step is real. Most people, if they think about the heliosphere at all, picture it as a kind of boundary marker, the edge of the solar system on a diagram. A dotted line past Neptune labelled with a technical name, something interesting to astronomers but not particularly relevant to the business of being alive. That picture is incomplete in an important way. The heliosphere is not a static boundary. It is a dynamic physical structure that the Sun is actively maintaining right now, at this moment, through a continuous process that has been running since the solar system formed. Understanding it changes what the solar system means. The Sun does not just emit light and heat. It also emits a continuous stream of charged particles, mostly electrons and protons, traveling outward in all directions at roughly 1 million miles per hour. This stream is called the solar wind, and it does not stop at any planet. It flows outward past Mercury, past Earth, past Jupiter, past Neptune, far into the outer reaches of the solar system. As it travels, it carries with it the Sun's magnetic field, stretched outward and wound into a spiral shape by the Sun's rotation. The solar wind and its embedded magnetic field form the heliosphere, a vast magnetic bubble that the Sun inflates around itself and everything that orbits it. Think of a boat moving through water. The boat pushes a wake ahead of it and a turbulent region behind. The Sun does something similar as it moves through the surrounding interstellar medium, the thin gas and magnetic field that fills the space between the stars. The solar wind pressure pushes outward against the interstellar medium. Eventually, far from the Sun, the solar wind runs out of force. It slows, stops, and the two pressures reach equilibrium at a boundary called the heliopause. Inside the heliopause is the heliosphere. Outside, it is interstellar space. The inner region where the solar wind is still supersonic is called simply the solar wind region. Further out, there is a zone called the termination shock, where the solar wind abruptly slows from supersonic to subsonic speeds as it encounters increasing resistance from the interstellar medium. Beyond that is the heliosheath, a turbulent compressed region before the heliopause itself. Voyager 1 crossed the termination shock in 2004 and the heliopause in 2012, measuring each transition in turn. What the heliosphere does for the solar system and for life is something most people never consider. It deflects galactic cosmic rays. These are high-energy particles arriving from sources throughout the galaxy. Supernova explosions, neutron stars, pulsar winds, other violent galactic events accelerated to significant fractions of the speed of light. When they encounter the heliosphere's magnetic field, many of them are scattered, deflected, and slowed. Not all of them. The heliosphere does not block everything, but it removes a large fraction of the most energetic particles before they reach the inner solar system. Without it, the radiation environment at Earth's orbit would be dramatically more intense. There is a conformation built into the Sun's own cycles. Every 11 years, the Sun goes through a cycle of increasing and decreasing activity. At solar maximum, the Sun's output is higher, the solar wind is stronger, and the heliosphere expands and strengthens. At solar minimum, the solar wind weakens, the heliosphere shrinks slightly, and more cosmic rays penetrate to the inner solar system. This fluctuation is measurable. During solar minimum, cosmic ray readings in the inner solar system go up. During solar maximum, they go down. The shield is not fixed. It breathes with the Sun, and when it weakens, the radiation environment inside responds. This is the thing no spacecraft currently carries a replacement for. The heliosphere is powered by a star. It is maintained by a star's continuous energy output across a volume of space spanning more than 100 astronomical units in every direction. There is no portable version of this. There is no spacecraft battery that can replace what the Sun does. A crew crossing the heliopause loses the protection immediately and permanently for as long as they remain outside it. Understanding what that exposure actually means requires understanding what the particles on the other side actually are. There is a quality to the heliosphere that becomes clearer when you consider what would happen without it. The Sun's solar wind is not the only thing flowing through the inner solar system. Interstellar neutral atoms also drift into the heliosphere from outside, carried by the Sun's motion through the interstellar medium. Some of these neutrals penetrate deep into the inner solar system before being ionized by solar radiation. NASA's IBEX mission, launched in 2008, mapped the boundary of the heliosphere by detecting energetic neutral atoms that were created at the heliopause and flew back into the inner solar system. This gave scientists a first global image of the heliosphere's outer boundary, not perfect, not complete, but the first picture of the structure from inside. What IBEX revealed and what subsequent observations have refined is that the heliosphere is not a smooth, symmetrical bubble. It is more complex. The Sun is moving through the local interstellar medium at roughly 26 kilometers per second, relative to the surrounding stars. This motion means that the heliosphere is compressed in the direction of travel, the nose of the heliosphere, pointing in the direction the Sun is moving, and elongated behind in the opposite direction, forming something like a comet shape. The nose is where the heliosphere meets the interstellar medium head-on. The tail region is where the deflected solar wind eventually mingles with the surrounding material. The IMAP mission, launched in September 2025, is designed to study this structure in much greater detail, using 10 instruments to map the heliosphere's boundary and the interaction between the solar wind and the interstellar medium with a precision not previously achievable. It will answer questions about the heliosphere's shape, its variation with the solar cycle, and how well it shields different regions of the solar system from galactic cosmic rays. What it cannot do is replace the heliosphere for a spacecraft that has left it. The heliosphere is not uniform. Some parts of it provide better shielding than others. The exact degree of cosmic ray reduction depends on where in the heliosphere you are, what phase of the solar cycle the Sun is in, and the energy of the particles involved. The 75 to 90% reduction figure is an average, not a constant. But even at the lower end of that range, it represents a radiation environment fundamentally more survivable than what Voyager measured outside. The radiation environment outside the heliosphere is not like the radiation most people think about when they hear the word. Most familiar forms of radiation are electromagnetic, X-rays, gamma rays, ultraviolet light. These are waves of energy that can ionize molecules, knock electrons out of atoms, and damage biological tissue, but they interact with matter in ways that shielding can address. Dense material absorbs them. Lead blocks X-rays. The Earth's atmosphere blocks ultraviolet. Add enough of the right material between the source and the target, and the intensity at the target drops. Galactic cosmic rays are not electromagnetic waves. They are matter. More specifically, they are atomic nuclei, atoms that have been stripped of all their electrons and accelerated to tremendous speeds by some of the most violent events in the galaxy. Most of them are protons, the nuclei of hydrogen atoms. A significant fraction are helium nuclei, and a smaller but critically important subset are the nuclei of much heavier atoms: iron, silicon, carbon, magnesium, oxygen. These heavier particles have a name in the field: HEE ions, where H stands for high, Z is the symbol for atomic number, and E stands for energy, high charge and high energy. Heavy, fast, and deeply penetrating. The origin of galactic cosmic rays is the violence of the galaxy. When a massive star exhausts its fuel and collapses, it explodes in a supernova, a release of energy so enormous that it briefly outshines entire galaxies. The shock waves from these explosions sweep through the interstellar medium for thousands of years, and as they travel, they accelerate particles. Protons, helium nuclei, and heavier particles get caught in the expanding magnetic fields of the shock waves and are repeatedly accelerated, gaining energy with each crossing until they reach fractions of the speed of light and escape into the interstellar medium. Neutron stars, pulsars, and other remnants of stellar death also contribute. The galactic cosmic ray background is a continuous isotropic rain of relativistic particles arriving from all directions, generated by the ongoing violence of stars dying throughout the Milky Way. When an Hz ion, a heavy nucleus traveling at say 50 or 70% of the speed of light, enters biological tissue, the damage it does is qualitatively different from X-ray or gamma-ray exposure. An X-ray passing through tissue scatters its energy broadly, ionizing molecules somewhat randomly along a path that spreads and diminishes. An Hz ion nucleus traveling at relativistic speed does something different. It travels in a straight line, and as it goes, it ionizes atoms densely and continuously along the entire length of its path through the tissue. The ionization density along the track is vastly higher than anything a conventional radiation source produces. The result is not scattered molecular damage. It is a continuous streak of destruction: chromosomes shattered, cell walls ruptured, the structural integrity of everything in the particle's path compromised in a single pass. The human body has evolved repair mechanisms for the kind of radiation it has been exposed to throughout evolutionary history. Those mechanisms handle the scattered, lower density damage of the radiation environment inside the heliosphere reasonably well. They were not calibrated against Hz ion tracks. The damage pattern is qualitatively different, and the repair systems are correspondingly less effective. Earth's own magnetic field provides a second layer of protection on top of the heliosphere. Astronauts on the International Space Station are still inside the heliosphere and still partially inside Earth's magnetic field. They receive elevated radiation compared to the ground, and this is monitored carefully. Their exposure is factored into career dose limits, but they are not receiving the full galactic cosmic ray spectrum. The Earth's magnetic field deflects a significant fraction of the lower energy portion, and the heliosphere has already removed the highest energy fraction before it reaches Earth's orbit at all. Outside the heliosphere, both layers are gone. The full galactic cosmic ray spectrum arrives unfiltered from every direction, and understanding what that means for any shielding system requires confronting something that physics does not give any easy answer to. The origin stories of galactic cosmic rays are worth dwelling on, because they connect the radiation environment of interstellar space directly to the most violent events in the galaxy's history. When a massive star exhausts its fuel, the collapse of its core releases more energy in a few seconds than the Sun will radiate in its entire 10 billion year lifetime. The shockwave that propagates outward from the collapsing core expands through the surrounding material at thousands of kilometers per second. As it travels through the interstellar medium over thousands of years, it sweeps up material and creates a region of turbulent, compressed magnetic field behind the shock front. Particles caught in this region undergo a process called diffusive shock acceleration. They repeatedly cross the shock front, gaining energy with each crossing, bouncing back and forth between the upstream and downstream regions of the shock, like a ping-pong ball between two approaching paddles. Each crossing adds energy. After many crossings, the particle has accumulated enough energy to escape the shock region entirely, and stream outward into the interstellar medium at a significant fraction of the speed of light. This process produces a characteristic energy spectrum, a power law distribution where more particles have lower energies and fewer have higher energies, but where particles of extremely high energy are continuously produced. The highest energy cosmic rays can carry energies that are, per particle, comparable to a fastball thrown by a professional baseball pitcher, compressed into a single subatomic nucleus. The energy density is not in the total number of particles. Interstellar space is not dense with them. It is in the energy per particle, which makes each one that reaches biological tissue a significant event. The Milky Way is estimated to host 1 to 2 supernovae per century on average. Each one contributes to the cosmic ray background for thousands of years after the explosion. As the shockwave expands and accelerates particles, the galactic cosmic ray environment is the accumulated output of all the supernovae that have occurred throughout the galaxy's history, ongoing continuously, refreshed by new explosions as old ones fade. It is not a static background, it is an active, galaxy-wide, billions of years old particle accelerator, and the heliosphere is what reduces its output to levels compatible with complex biology in our corner of the solar system. The instinctive engineering response to a radiation problem is to add shielding. It works for most forms of radiation: X-rays, gamma rays, neutrons from a reactor, solar flare particles. These can all be reduced by adding dense material between the source and the target. The principle is simple. The particle enters the shielding material, loses energy in interactions with atoms along the way, and eventually stops before it reaches the other side. More material means more interactions, means more energy loss, means a lower dose at the target. Lead stops X-rays. Water stops neutrons. Thick aluminum reduces solar particle events to manageable levels. For the highest energy, Hc cosmic rays, this logic does not apply in the same way. It applies partially, and the part where it stops applying is the part that makes the problem genuinely hard. When a very high energy Z nucleus, an iron nucleus say, traveling at 60% of the speed of light, enters a thick shield made of dense material, it does not simply slow down and stop. It has enough energy to travel deep into the material before it encounters a nucleus of the shielding material directly. When that collision happens, the outcome is not the H particle stopping quietly. The collision shatters both nuclei, the original Hc particle fragments, into multiple smaller particles. The nucleus of the shielding material also fragments, and the energy that was carried by the original particle is now distributed among a spray of secondary particles moving outward from the collision point. Protons, neutrons, lighter nuclear fragments, pions, and gamma rays. This spray of secondary particles is called a secondary particle cascade, produced by a process called nuclear spallation, and the secondary particles fan outward from the collision point in all directions, including inward, toward the crew compartment that the shielding was supposed to be protecting. The problem is not that secondary particles are always worse than the original. For low-energy cosmic rays, shielding does help, and the secondary cascade is less intense than the primary particle. But for the highest energy Z particles, the secondary cascade can deliver a radiation dose inside the shielded area that is comparable to or exceeds what the unshielded particle would have delivered. The shield has, in a meaningful sense, taken one dangerous particle and converted it into several particles, some of which reached the crew anyway. This is not a hypothesis, it is a consequence of nuclear physics that is well understood. The problem has a name in the field. It is called secondary radiation, and it is one of the reasons that NASA's Human Research Program identifies galactic cosmic ray protection as the most critical unresolved health risk for long-duration spaceflight beyond the heliosphere. Think of it this way: a cannonball fired at a wall of marbles will stop in the wall, but the marbles scatter from the impact point in all directions. If the crew compartment is behind the marble wall, some of the scattered marbles reach it. The wall stopped the cannonball but created a new projectile problem. For the highest energy cosmic rays, this analogy is not a perfect description of the physics, but it captures the character of the problem. Dense shielding material interacts with the incoming particle in ways that produce a secondary threat rather than simply absorbing the primary one. There is a practical consequence of this. Adding more passive shielding beyond a certain thickness does not necessarily reduce the biological dose inside the spacecraft. In some configurations, it increases it. There is an optimal shielding thickness for a given radiation environment, beyond which additional material makes things worse. For the galactic cosmic ray environment outside the heliosphere, that optimal thickness is less protection than would be needed for a multi-year mission. The obvious alternative is to deflect the particles before they reach the shielding at all, not absorb them, deflect them. This is in principle what the heliosphere does. It uses magnetic fields to scatter and redirect charged particles before they penetrate deeply into the solar system. A spacecraft could in principle generate its own magnetic field for the same purpose. But understanding why that is harder than it sounds requires understanding something specific about how the heliosphere works. The specific physics of how the secondary cascade develops is worth understanding in more detail, because it clarifies why the problem is not simply a matter of finding the right material or the right thickness. When a high-energy ETS-EE nucleus enters shielding material, the first thing that happens is ionization. The particle strips electrons from atoms in the material along its path, losing some energy in the process. For a proton, this continuous ionization can eventually slow and stop the particle in a sufficiently thick shield. This is how proton therapy for cancer works. Protons can be targeted to deliver their energy at a precise depth, stopping in a tumor rather than continuing through the body. For an Hz ion nucleus at galactic cosmic ray energies, the continuous ionization is not sufficient to stop the particle. The nucleus carries too much momentum and too much energy. It will ionize atoms along its path, losing energy gradually, but it will also eventually encounter an atomic nucleus of the shielding material in a direct collision. When that collision happens between a relativistic ion nucleus and, say, an aluminum nucleus in the wall of a spacecraft, the result is nuclear fragmentation. Both nuclei shatter. The original iron nucleus breaks into smaller fragments, lighter nuclei like carbon, helium, or hydrogen moving at high speeds. The aluminum nucleus also breaks apart. The energy that was concentrated in one projectile is now distributed among many smaller ones. The smaller secondary fragments carry less individual energy, but more collective penetrating power. Lighter nuclei with high energies can travel further through material than the original heavy nucleus would have. Some of them are neutrons, which carry no charge and are therefore unaffected by further electromagnetic interactions with the shielding material. They pass through it directly. The secondary neutrons propagate into the crew compartment. There they interact with hydrogen nuclei in biological tissue, transferring energy that causes cellular damage. The bottom line is that for very high energy Z particles, thicker shielding means more secondary particle production, which means more neutrons, which means a higher dose in the crew compartment from neutron interactions. There is an optimal shielding configuration that minimizes the total biological dose, and that configuration involves less shielding than you might naively want to add. Adding shielding beyond that optimal point increases the biological hazard. This is not a marginal effect. For some particle energies and shielding geometries, the secondary cascade can dominate the total dose at the crew position. The intuition that more shielding equals more protection fails specifically and substantially for the portion of the cosmic ray spectrum most relevant to missions outside the heliosphere. The heliosphere deflects cosmic rays, but it does not do so because its magnetic field is strong. The heliospheric magnetic field, measured by Voyager at the termination shock and in the heliosheath, is extremely weak by any laboratory standard. At those distances, it is on the order of a fraction of a nanotesla, roughly 100,000 times weaker than Earth's surface magnetic field, and immeasurably weaker than any magnet you would encounter in everyday life. By field strength alone, the heliospheric magnetic field is negligible. What the heliosphere has is not strength, it is volume. When a cosmic ray particle enters the heliosphere at the heliopause, it does not pass through the magnetic field in a fraction of a second. It spends months traveling through it, following a curved and wandering path as the field deflects and scatters it across hundreds of astronomical units. The deflection is gradual and cumulative. A very small force, applied over a very long path, produces a significant change in direction. The particle that entered the heliosphere aimed at one point in the inner solar system exits aimed somewhere different, having been redirected by the accumulated effect of billions of interactions with a weak but vast magnetic field. This is the key physical insight. Deflecting a relativistic particle magnetically does not require a strong field. It requires a large field, one that the particle travels through long enough for the deflection to accumulate to a useful angle. A spacecraft's magnetic shield cannot provide this. No matter how powerful the superconducting coils, no matter how strong the field they generate around the ship, the field occupies a region measured in meters. A cosmic ray particle traveling at half the speed of light passes through 10 meters in roughly 60 nanoseconds, 60 billionths of a second. The deflection accumulated in that time is negligible for the highest energy particles, regardless of field strength. The heliosphere works because it is the size it is. It works because the Sun continuously expends enormous energy to maintain a magnetic environment spanning more than 100 astronomical units. There is no portable version of this, in the same way there is no portable version of a mountain. Size is the mechanism. A spacecraft can carry field strength. It cannot carry volume. This is why the search for alternatives has turned to active shielding research. Not the passive shielding of material walls, but the active generation of magnetic fields to deflect incoming particles. The physics principle is real. Charged particles follow curved paths in magnetic fields. If the field is strong enough and the geometry is right, particles can be deflected around the spacecraft rather than into it. The research programs exist. The challenge is what they've found, which is where the next layer of the problem lives. The mathematics of magnetic deflection are useful to make concrete because they show why field strength alone cannot substitute for the heliosphere's volume. The path a charged particle follows in a magnetic field is governed by the Lorentz force, the force that the magnetic field exerts on a moving charged particle. The radius of the curved path the particle follows, called the gyroradius, is directly proportional to the particle's momentum and inversely proportional to the product of its charge and the magnetic field strength. A stronger field curbs the path more tightly. A heavier, faster particle has a larger gyroradius and is harder to curve. For a relativistic ion nucleus at galactic cosmic ray energies, one of the most damaging particles in terms of biological impact, the gyroradius in the heliospheric magnetic field is on the order of astronomical units. The particle's path is curved, but so gently that crossing 100 astronomical units of heliospheric field is what accumulates meaningful deflection. The heliosphere works by providing hundreds of astronomical units of field for the particle to traverse. Now consider a spacecraft magnetic shield, generating a field 10,000 times stronger than the heliospheric field over a radius of 10 meters. The particle's gyroradius in that field is approximately 10,000 times smaller than in the heliospheric field, but the region of field the particle transits is 10 meters, not hundreds of astronomical units. The ratio of transit distance to gyroradius, which determines the total deflection angle, is not more favorable for the spacecraft shield. It is roughly the same or worse depending on the specific particle energy. Stronger field, smaller volume. The product that matters for deflection, field strength times transit distance, is not improved. This is why active shielding research has not produced a viable design despite decades of effort. The fundamental physics of magnetic deflection for the particle energies involved requires either an enormous volume, which a spacecraft cannot carry, or a field strength so extreme that it cannot be generated with any known or projected technology at spacecraft mass budgets. There is one more feature of the heliosphere's deflection mechanism that is worth understanding, because it explains why the Sun's activity cycle directly affects how well the inner solar system is protected. The solar wind does not flow uniformly in all directions at all times. During periods of high solar activity, solar maximum, the Sun emits more particles at higher speeds. The heliosphere inflates and its magnetic field strengthens. During solar minimum, the wind weakens. The heliosphere contracts slightly and the magnetic field in the heliosheath becomes less effective at scattering galactic cosmic rays. This means that the protection the heliosphere provides fluctuates with a roughly 11-year cycle. Cosmic ray detectors on Earth and on spacecraft in the inner solar system show this fluctuation clearly. During solar minimum, cosmic ray flux in the inner solar system is measurably higher than during solar maximum. The difference is not enormous. We are talking about variations within the already shielded inner heliosphere. But it is real, directly measurable, and confirms that the heliosphere's protective function is dynamic and dependent on ongoing solar activity. For a spacecraft that has crossed the heliopause, this solar cycle variation is irrelevant. The spacecraft is outside the heliosphere entirely. The question of whether the Sun is currently at maximum or minimum does not change the radiation environment in interstellar space. The protection is gone regardless of where in the solar cycle the departure occurred. Active magnetic shielding for spacecraft is a real research area. It is not science fiction. The concept is straightforward. Place superconducting coils around or within the spacecraft to generate a magnetic field and let that field deflect incoming cosmic ray particles before they reach the crew compartment. Several research groups at NASA, ESA, and universities have investigated this. The basic physics is not in question. Charged particles and magnetic fields follow curved paths. If the field is strong enough and the geometry is right, it can in principle redirect a significant fraction of incoming particles away from the protected volume. The challenges that have emerged from this research are specific and they have not been resolved. The first is mass. Superconducting coils capable of generating a field strong enough to provide meaningful deflection at the energies of galactic cosmic rays require large amounts of superconducting material, heavy cooling systems to keep the superconductor at operating temperature, and structural support to maintain the coil geometry under the magnetic forces the coil itself generates. The mass of such a system, for any configuration that provides useful protection, is many times larger than any spacecraft currently launched or planned. The coils alone would likely exceed the total mass budget of any realistic near-future mission. The second is power. Maintaining a superconducting magnetic system in space requires power to run the cooling, to maintain the current, to handle any quench events where the superconductor temporarily loses its superconducting property. The power demand is not trivial, and a spacecraft operating beyond the solar system cannot use solar panels as its primary power source. Radioisotope power systems generate limited power. The energy budget for active shielding competes directly with the energy budget for everything else the spacecraft needs to do. The third is geometry. A magnetic field deflects charged particles, but the deflection depends on the angle at which the particle enters the field. A field that protects efficiently against particles coming from directly ahead provides less protection against particles arriving from the sides or behind. Cosmic rays arrive from all directions simultaneously. A geometry that provides omnidirectional protection while also being physically realizable on a spacecraft has not been demonstrated. The fourth is neutrons. When the secondary particle cascade from a thick shield produces neutrons, which it does because nuclear spallation reactions produce neutrons, those neutrons are electricity neutral. Magnetic fields deflect charged particles. They do not deflect neutral ones. A magnetic shield that redirects incoming protons and Hz ions does nothing for the neutron component of either the direct cosmic ray flux or the secondary cascade. Neutrons are biologically damaging. They require dense hydrogen-rich materials to moderate and absorb. A complete solution to the radiation problem requires addressing both the charged particle and the neutron components, and no single technology addresses both simultaneously. The IMAP mission, launched in September 2025, is designed to study the heliosphere boundary and the interaction between the solar wind and the interstellar medium. It will expand our understanding of how the heliosphere functions as a protective system. What it does not do is provide a spacecraft-scale equivalent of what the heliosphere provides. It is a mission of understanding. The gap between understanding a natural shield and building an artificial one at the same scale remains as wide as it was before the mission launched. No active magnetic shielding system has been deployed on any human spaceflight. No active shielding system is on the manifest for any near-future crewed mission. The research programs have not converged on a design. The problem is not that scientists are not working on it. The problem is that the physics of what is needed and the engineering of what can be built are currently separated by a substantial gap. The neutron problem in active shielding deserves additional emphasis because it is often overlooked in popular discussions of the topic. When people imagine magnetic shielding for a spacecraft, they typically picture a force field that blocks particles from reaching the ship. The magnetic field deflects charged particles, protons, helium nuclei, Hz ions, by exerting a force on them. This part of the concept is physically valid. But the galactic cosmic ray environment is not exclusively composed of charged particles. The secondary cascade from any interaction between cosmic rays and shielding material produces neutrons. Cosmic ray interactions with the nuclei in the interstellar medium also produce neutrons as secondary products, and some cosmic ray events produce neutrons directly. Neutrons carry no electric charge. A magnetic field exerts force proportional to charge. Zero charge means zero magnetic force. A neutron entering a spacecraft's magnetic field follows a straight line regardless of field strength. The field is transparent to it. In the crew compartment, neutrons interact primarily with hydrogen nuclei, which are abundant in biological tissue, in water, in organic molecules. When a fast neutron strikes a hydrogen nucleus, it transfers some of its energy to the proton, which recoils and causes ionization damage in the surrounding tissue. This is called neutron dose, and it is a significant component of the radiation hazard in any environment with high-energy particle interactions. To moderate and absorb neutrons, you need hydrogen-rich material, polyethylene, water, hydrogen-rich pineal, polyethylene, water, hydrogen-rich polymers. These materials slow neutrons down through repeated collisions with hydrogen nuclei until the neutrons are absorbed. But hydrogen-rich materials are not dense enough to stop high-energy charged particles, and dense materials that stop charged particles are poor moderators for neutrons. A complete radiation solution must address both charged particles and neutrons simultaneously. No single technology does this. An effective shield would require a layered approach combining magnetic deflection for charged particles and thick hydrogen-rich material for neutron moderation. And the secondary cascade from the charged particle shielding produces more neutrons for the hydrogen layer to absorb. The two parts of the solution work against each other in terms of the problem they create for the other component. The radiation problem exists at any speed. You could in principle move very slowly across the heliopause and still encounter the full galactic cosmic ray environment on the other side. The radiation is always there. The shielding problem is always real, but any mission that intends to actually reach another star, not just cross the heliopause and return, but travel to the nearest stellar system, faces a separate problem that arises specifically because of the speed the mission requires. Consider the geometry. Alpha Centauri, the nearest star system to our own, is approximately 4.25 light-years away. At Voyager 1's current speed, roughly 61,000 km per hour, or about 17 km per second, the trip would take approximately 75,000 years. No crew could survive that. No mission architecture could sustain biological life across that timescale. If the goal is to send humans to another star in a time that means anything to the humans who launch and the civilization that sends them, the required speed is a significant fraction of the speed of light, not 10%, possibly 20%, 30% or more. This is where something changes. Interstellar space is not empty. It contains gas, on average roughly 1 hydrogen atom per cubic centimeter, far less dense than any vacuum achievable in an Earth laboratory, but not nothing. At the speeds of ordinary spaceflight, this gas is irrelevant. A spacecraft moving at a few tens of kilometers per second encounters so few atoms that the cumulative effect over years is negligible. At 20% of the speed of light, this changes. From the spacecraft's reference frame, the ship is stationary and the interstellar medium is approaching at 20% of light speed. The kinetic energy of a proton traveling at 20% of light speed is not negligible. It is a high-energy particle, and the spacecraft, moving continuously through the medium, is continuously encountering these particles, not one at a time in some rarefied cosmic event, continuously at every moment of the flight, across whatever distance the mission covers. Published research specifically on radiation conditions in relativistic interstellar flight has calculated what this means in concrete terms. At speeds between 20 and 40% of the speed of light, the absorbed dose rate from interstellar hydrogen gas alone, before adding any contribution from galactic cosmic rays, could reach hundreds to thousands of rems per second in an unshielded crew section. A dose of 600 rems delivered to the whole body is considered lethal. At the lower end of those estimates, a crew member would receive a lethal dose in approximately 1 second of flight at 20% of light speed without protection. The heliospheric shielding problem is a steady background radiation issue. The interstellar medium at speed is an acute, overwhelming, continuous assault from the front of the spacecraft. No passive shielding solves this. Adding material to the front of the spacecraft creates the secondary cascade problem described earlier. Magnetic deflection might reduce the charged particle component, but neutrons from the cascade are not deflected. And unlike the background cosmic ray problem, this one scales directly with speed. The faster the spacecraft moves to reduce the travel time, the more intense the forward particle flux becomes. There is a speed range, somewhere between a few percent and 20% of light speed, where the interstellar medium becomes the dominant radiation hazard. Below it, the galactic cosmic ray background dominates. Above it, the interstellar medium becomes lethal from the front. The mission is caught between two dangers that bracket the useful speed range from different directions. This is the speed trap. Go slow enough to survive the interstellar medium, and the trip takes tens of thousands of years. Go fast enough to make the mission meaningful, and the interstellar medium kills you from the front. The window in between, if it exists at all for an unshielded crew, is narrow and poorly characterized. The relationship between mission speed and the interstellar medium radiation problem has a specific structure that is worth mapping clearly. At very low speeds, below perhaps 1% of light speed, the interstellar medium is not a radiation concern. A spacecraft moving at 1% of light speed encounters hydrogen atoms at an effective energy that, while higher than at rest, is not immediately dangerous and can be managed with modest shielding. At these speeds, the galactic cosmic ray background is the dominant radiation problem. The crossing of the heliopause and the loss of heliospheric protection matters most. As speed increases past roughly 5 to 10% of light speed, the interstellar medium begins to contribute meaningfully to the forward radiation flux. The effective particle energy of approaching hydrogen increases rapidly, since kinetic energy scales with the square of velocity. At 10% of light speed, the energy per proton is already in the range where it constitutes an ionizing radiation hazard. At 20%, the dose rate from the medium alone becomes comparable to or exceeding the galactic cosmic ray background. Above roughly 20% of light speed, the interstellar medium problem dominates. The forward particle flux is the primary radiation hazard. Adding shielding to the front of the spacecraft creates the secondary cascade problem. The dose rate is high enough that an unprotected crew would accumulate a lethal total dose very quickly. The implication is that there is, in principle, a speed range somewhere between roughly 5 and 20% of light speed, where both problems are present but neither is instantly lethal. Below this range, the trip takes too long for a human mission. Above it, the interstellar medium overwhelms any practical shielding. Within it, the galactic cosmic ray background and the forward particle flux are both present and both dangerous, but potentially manageable with adequate shielding for some mission durations. Whether this window actually exists in a way that allows a survivable mission with realistic engineering has not been demonstrated. The calculations are model dependent, the shielding configurations are not optimized, and the biological tolerances at extended exposures in this environment are not from direct measurement. The window is theoretical, it is narrow, and threading it requires solving the shielding problem, the active shielding problem, and the biological adaptation problem simultaneously. Most people, thinking about leaving the solar system, picture the outer boundary as the heliopause, perhaps the Kuiper belt, the ring of icy bodies beyond Neptune. Cross those and you are in open interstellar space with nothing but the long void between you and the next star. This picture is missing something large. The solar system does not end at the heliopause. Gravitationally, it extends far beyond it, much further than most people realize, into a region that has never been directly observed, but whose existence we infer from the behavior of comets. Long-period comets, the ones that appear in the inner solar system, with orbital periods of thousands or millions of years, come from somewhere. Their orbits, when traced backward, trace back to an enormous spherical shell of icy bodies surrounding the entire solar system, at distances estimated to range from roughly 2,000 to 100,000 astronomical units from the Sun. This structure is called the Oort cloud, named for the Dutch astronomer Jan Oort, who proposed its existence in 1950 based on the orbital dynamics of observed comets. To put that in perspective, the heliopause is at approximately 120 astronomical units. The inner edge of the Oort cloud is estimated to begin at around 2,000 astronomical units. There is a gap between those numbers, a region between the heliopause and the Oort cloud that is genuinely interstellar space, unoccupied by significant solar system material. But beyond that gap, the solar system's gravitational influence continues, loosely, for a vast distance. The outer edge of the Oort cloud is estimated at roughly 100,000 astronomical units, close to 2 light-years from the Sun. Nearly halfway to Alpha Centauri, the Oort cloud is estimated to contain trillions of objects. Most are small, icy bodies left over from the formation of the solar system, ranging from pebbles to bodies many kilometers across. They're spread across an enormous volume, and their average separation is large. A spacecraft traveling on a random trajectory through the Oort cloud would almost certainly encounter nothing. The cloud is far more empty than dense. At the speeds relevant to any meaningful interstellar mission, however, this changes the calculation. At 10% of the speed of light, 30,000 kilometers per second, a dust grain massing 1 milligram carries kinetic energy of roughly 450 gigajoules. The atomic bomb dropped on Hiroshima released approximately 63 terajoules, or 63,000 gigajoules. A milligram of dust at 10% of light speed delivers roughly 1/10 of 1% of that energy. Not a nuclear weapon, but focused onto a microscopic impact point on a spacecraft hull. It is not nothing. A gram-mass pebble at the same speed carries roughly 450 terajoules, comparable to a small nuclear device delivered instantaneously to whatever it strikes. The Oort cloud's average density is very low. Most trajectories through it will not encounter anything significant, but the uncertainty about the actual distribution of small objects at those distances is substantial. We have not observed the Oort cloud directly. Our estimates come from the orbital dynamics of the comets it sends our way. Whether the distribution contains enough small, undetectable objects to pose a statistical threat to a high-speed spacecraft is genuinely unknown. At the impact energies of relativistic travel, a collision that would be harmless at ordinary spacecraft speeds becomes catastrophic. A mission traveling at speeds necessary for any meaningful interstellar mission cannot reduce speed to navigate carefully through the Oort cloud region. Slowing down means extending the mission by years or decades. The threat is uncertain. The consequence of a hit is potentially mission-ending, and the hit cannot be detected and avoided at those speeds because the object would be invisible at long range, and the closure speed would leave no time for evasion. This is not a certain danger. It is an unknown one, and at the velocities of interstellar travel, unknown dangers with catastrophic consequences are their own catastrophic consequences. The Oort cloud collision hazard at interstellar speeds is difficult to characterize precisely because we have never directly observed an Oort cloud object. Every estimate of the cloud's population, density, and size distribution is derived from inference rather than direct measurement. What we observe is long-period comets. When a comet enters the inner solar system with an orbital period of thousands or millions of years, its orbit traces back to the outer reaches of the solar system. The statistical distribution of these orbital parameters, the directions they come from, the energies they carry, the distribution of their orbital periods, constrains the overall structure of the source population. Jan Oort's original 1950 analysis of these distributions led to the inference that there must be a vast, roughly spherical reservoir of icy bodies at large distances from the Sun, occasionally perturbed by passing stars or the gravitational tide of the Milky Way into trajectories that bring them sunward. The total number of objects in the Oort cloud is estimated by working backward from the flux of long-period comets observed, and accounting for the fraction of Oort cloud objects that would be perturbed onto observable trajectories within any given period. The estimates are highly uncertain. The population could range from hundreds of billions to several trillion objects, depending on assumptions about the efficiency of perturbation and the survival rate of comets in the inner solar system. The size distribution of Oort cloud objects is also uncertain. Most are probably small, pebble to boulder scale, but there are likely objects of kilometer scale and larger, like Pluto-sized bodies scattered through the cloud at low density. The collision hazard for a high-speed spacecraft depends on the density of objects in the size range that would cause catastrophic damage at the spacecraft's speed. At 10% of light speed, the kinetic energy threshold for catastrophic damage is very low. A gram-scale object would release energy comparable to a small bomb. Whether there are enough such objects along any given trajectory through the Oort cloud region to make a collision statistically probable over the transit distance is not known. What we know is that we do not know enough to confidently say the hazard is negligible. Every danger discussed so far, radiation, shielding failure, the interstellar medium at speed, the Oort cloud, is a danger to physics and engineering. These are problems of particles and materials and energies. But there is a context inside which all of these problems exist, and that context is biology. The human body, and the biology was not consulted when the universe arranged these hazards. The human body is a product of 4 billion years of evolution inside a very specific set of environmental conditions. Inside the heliosphere, on a planet with a magnetic field, under an atmosphere, in one gravity, the body's chemistry, its repair mechanisms, its tolerances for stress and radiation and deprivation, all of these were selected by evolution against the conditions that actually existed. The conditions that existed were the conditions of Earth and its immediate space environment, not the conditions of interstellar space. Consider what we already know from the most extreme space environment humans have entered: low Earth orbit. Astronauts aboard the International Space Station are inside the heliosphere. They are still partially protected by Earth's magnetic field, which deflects a significant portion of cosmic rays at lower energies. They are living in microgravity, not zero gravity. The station is in continuous freefall and the effective gravity inside is very close to zero. After 6 months aboard the station, astronauts return to Earth with measurable consequences. Bone density loss of roughly 1% per month, muscle atrophy, cardiovascular deconditioning, fluid shifts from the lower body to the upper body that increase intracranial pressure and cause changes in the shape of the eye, leading to visual acuity changes that can persist for months after return. Some of these changes reverse with rehabilitation. Some, particularly the visual changes, do not fully reverse in some individuals. 6 months. In the most protected, most supported, most carefully monitored environment humans have ever created in space. With exercise regimens, nutritional supplements, pharmaceutical countermeasures, and medical staff on Earth available for real-time consultation, an interstellar mission would not be 6 months. At speeds viable for a meaningful mission, a transit to Alpha Centauri would be measured in decades, possibly a century. The biological deterioration from microgravity alone, projected across those timescales without the countermeasures available on the ISS, is severe. The radiation environment outside the heliosphere, without adequate shielding, compounds the problem across every biological system simultaneously. Hz ion damage is cumulative. Each particle that passes through tissue leaves a track of damage. The repair mechanisms that handle this damage were designed for a much lower rate of Hz exposure than the full galactic cosmic ray spectrum delivers. Over years of exposure, the accumulated damage to DNA, to cell membranes, to the nervous system, and to the cardiovascular system reaches levels that current risk models project as causing substantial increases in cancer incidence and possible central nervous system effects that have no parallel in any studied population. NASA's Human Research Program, which coordinates research into the health risks of long-duration spaceflight, identifies galactic cosmic ray exposure as the most critical unresolved problem for missions beyond Earth's magnetosphere. Not solar radiation, not microgravity, the specific radiation environment that only becomes the primary hazard outside the heliosphere. Mars mission concepts of roughly 900 days are currently considered near the ceiling of what current shielding and countermeasures can manage before radiation and physiological risks become unacceptable. An interstellar mission is not 900 days. An interstellar mission is orders of magnitude longer. The body is not built for what that requires. The rate of physiological change in microgravity is not uniform across body systems. Some systems adapt rapidly and then stabilize. Others continue to change throughout the duration of exposure. Understanding which processes would dominate over the timescales of an interstellar mission requires extrapolating well beyond the mission durations of current spaceflight data. The longest continuous human spaceflight on record is approximately 437 days, achieved by Soviet cosmonaut Valery Polyakov aboard the Mir space station. This is the ceiling of direct human data for microgravity physiology. The documented effects at this duration include substantial bone density loss, significant muscle atrophy, cardiovascular deconditioning, immune system changes, and the visual acuity changes from intracranial pressure shifts mentioned earlier. For mission durations beyond roughly 14 months, physiological modeling must extrapolate from trends observed in shorter missions. The models predict continued bone loss, but the rate may slow as the skeleton reaches a new equilibrium. The models predict continued cardiovascular effects. The radiation damage continues to accumulate at a roughly constant rate. Since it is driven by the cosmic ray flux rather than any body adaptation, what is not known is whether long-term exposure to elevated galactic cosmic ray radiation produces effects qualitatively different from those predicted by linear dose response models. Some evidence from animal studies suggests that HC radiation may produce non-linear biological effects, cascades of cellular responses that amplify the damage beyond what a simple dose calculation would predict. The central nervous system effects of HC radiation are of particular concern. Since neurons are post-mitotic, they do not replicate, and therefore cannot replace damaged cells the way other tissues can. The biological hazard of an interstellar mission is not simply the sum of known hazards scaled up in proportion to mission duration. It involves extrapolation into a regime where the physics of the radiation environment is well understood, but the biological response is not, and where the duration of exposure exceeds any direct human data by orders of magnitude. There is one more dimension to these dangers that makes each of them harder than it would be in any other context. On a mission in low Earth orbit, a hardware failure triggers a cascade of well-practiced emergency procedures. The crew has options. They can shelter in place. They can attempt repairs. In a serious failure, they can board a return vehicle and be on the ground in hours. The mission architecture assumes that rescue is possible. Everything in the design of the life support, the redundancy of critical systems, the protocols for emergencies, all of it is built around the assumption that if the worst happens, help can come. On a mission to the moon, the timescale stretches, and emergency evacuation takes days, not hours. The Apollo program demonstrated this. When Apollo 13 suffered its oxygen tank failure, the crew had to improvise life support solutions, and the flight took 4 days to return. The situation was dangerous. The crew survived because the physics allowed a return on that timescale. On a mission to Mars, the timescale stretches further. A crew at Mars during a medical emergency cannot be reached for months. Any resupply would require planning and launch windows months in advance. The mission would need to be largely self-sufficient. This is a serious and currently unsolved challenge for Mars programs. But it is bounded. Mars is within the solar system. Earth is reachable in principle, even if not quickly. On an interstellar mission, the concept of rescue ceases to have practical meaning. At 1 light-year from Earth, a tiny fraction of the distance to Alpha Centauri, barely past the inner edge of the Oort cloud, a signal sent from the spacecraft takes 1 year to reach Earth. A response takes another year to return. A round-trip communication takes 2 years. If the crew faces a medical emergency and sends a distress call, any useful response from Earth arrives 2 years later. By then, the emergency has either been resolved by the crew, or it has not been resolved at all. The crew cannot wait 2 years for advice. At the full distance to Alpha Centauri, 4¼ light-years, a round-trip communication takes more than 8 years. A crew that reports a hardware failure will wait more than 8 years for any response. The response cannot include a part that was forgotten. It cannot include a specialist who is not aboard. It cannot include a rescue mission. Even if Earth launched a rescue ship, the moment the distress call arrived, the ship would take decades to arrive. This means the mission carries the entirety of its own solution. Space. Every spare part, every medical supply, every technical expertise, every contingency response These must all be on board at departure. There is no resupply. There is no second opinion from a specialist who was not packed. There is no abort option that leads to safety within any human lifetime. If something fails that the crew cannot fix, it stays failed. This is not a psychological observation about loneliness. It is an engineering and medical constraint. Every risk that exists on an interstellar mission is amplified by the complete absence of any external mitigation. The radiation problem is harder because there is no hospital. The mechanical failure problem is harder because there is no supply chain. The biological deterioration problem is harder because there is no flight surgeon with access to updated research and new treatments. Every danger described in this script is a danger without a safety net. The isolation does not create new problems. It makes every existing problem worse. The isolation problem has a psychological dimension that is worth naming separately from the operational and engineering dimensions. Human beings are social organisms. The evolutionary history of the human brain selected strongly for social cognition, for group coordination, for the ability to read and respond to the emotional states of other people. Long-duration isolation from any social contact beyond the mission crew has documented psychological effects. These effects are not simply discomfort. They include cognitive changes, reduced problem-solving performance, altered risk assessment, decreased motivation that become relevant to mission safety over extended durations. The longest studies of small group isolation in confined environments conducted by analog missions in Antarctica, in submarine deployments, and in dedicated isolation studies for space mission research show consistent patterns. After the initial period of adjustment, groups establish social hierarchies and communication patterns. Tensions develop and are managed. But over months to years, the cohesion of small isolated groups tends to degrade without external social input. The maintenance of healthy group function requires deliberate intervention, communication protocols, structured activities, conflict resolution mechanisms that cannot be improvised when the group is already stressed by other mission demands. For an interstellar mission, the crew would be isolated not just from humanity as a whole, but from any meaningful real-time communication with anyone outside the ship. The communication delay makes the isolation absolute in functional terms. Messages from Earth arrive months or years after they were sent, describing events that have since passed. They cannot substitute for the social support that human psychology requires. The crew is, in the deepest sense, alone together for the entire mission duration. The psychological problem does not add a new physical barrier. It adds a human dimension to every existing barrier. The radiation exposure is experienced by people under psychological stress. The hardware failures occur in a context of social tension. The medical decisions are made by isolated individuals without the support structures that inform medical decision-making in any other context. The isolation amplifies the consequences of every other risk by affecting the human capacity to manage those risks. The barriers to leaving the solar system can be separated into categories based on their current state, and doing so is more useful than simply listing them as equal dangers. Some of them are genuine engineering problems. They are hard, but they have a path forward in principle. Life support systems capable of functioning for decades without resupply. This is a hard engineering problem. But it is not a physics problem. The physics of closed-loop life support is understood. Building a reliable implementation across multi-decade timescales is an enormous engineering challenge. Communication systems capable of maintaining useful data transmission across light years. This is also solvable in principle with phased arrays, high-power lasers, and long integration times. Navigation across interstellar distances, accounting for the motion of the destination star relative to the Sun. This requires precision but is within reach of current astrometry. These are problems that future engineering could plausibly address. Other barriers are currently at the limit of known physics with no identified solution path. The secondary particle cascade from passive shielding is not an engineering problem. It is a consequence of nuclear physics. The problem has been understood for decades, and no material configuration has been found that eliminates it for the highest energy particles while maintaining structural feasibility. The neutron component of both the cosmic ray flux and the secondary cascade is unaffected by magnetic fields. The active magnetic shielding concepts face mass, power, and geometry challenges that current technology cannot meet, and that no proposed technology roadmap confidently resolves. The interstellar medium particle flux at relativistic speeds has no known engineering mitigation. These are not problems waiting for better materials or more funding. They are problems where the current best understanding of physics does not offer a clear path. A third category contains problems that may require physics that does not currently exist. A propulsion system fast enough to make interstellar travel meaningful within a human lifetime, while slow enough to avoid the lethal interstellar medium effects at higher speeds, requires operating within a window that may be physically narrow. Whether that window can be threaded with any propulsion concept compatible with the mass and energy budgets of a launchable spacecraft is genuinely unknown. Solutions in this category are not around the corner. They require ideas that have not yet been had. Understanding which category each barrier falls into is not defeatist. It is the beginning of any honest research program. The barriers that are engineering problems deserve engineering investment. The barriers that are physics limit problems require fundamental research into physics, not more shielding material. And the barriers that may require new physics deserve the kind of sustained theoretical attention that produce the physics currently being applied everywhere else. The distinction between engineering problems and physics limit problems matters not just theoretically, but practically, because it determines where research investment can make a difference. For the engineering problems, life support, communication, navigation, or cloud deflection at lower speeds, the path forward is development. More reliable, closed-loop life support systems, higher power laser communication arrays, more precise astrometric measurements of target star positions and motions, deflection systems for debris in the speed range where kinetic impacts are survivable. These are hard engineering challenges, but they are the kind of challenges that have historically yielded to sustained investment and incremental progress. The history of spaceflight is largely a history of solving engineering problems that seemed impossibly hard from the outside. For the physics limit problems, the secondary cascade, the neutron component of the radiation hazard, the interstellar medium at high speed, the path forward is not development of existing approaches. It requires finding new physical principles that have not yet been identified. This is fundamentally different work. It is closer to the work that preceded the development of nuclear power or transistors. Not engineering a known principle, but discovering a principle that does not yet exist in the literature. This kind of work is unpredictable in timeline, uncertain in outcome, and cannot be accelerated simply by spending more money on a known approach. Understanding this distinction helps clarify what a realistic research agenda for interstellar human spaceflight actually looks like. Investing in advanced life support is useful and appropriate. Investing in more studies of passive shielding configurations for high-energy cosmic rays is unlikely to produce a breakthrough because the constraint is the secondary cascade physics, not the choice of material. Investing in the fundamental physics of magnetic deflection at spacecraft scales, in the biology of 8Z radiation damage, and repair in the thermodynamics of long-duration closed ecosystems. These are investments that might produce the kind of new knowledge from which genuine solutions could emerge even if the timeline cannot be predicted. The categorization also has implications for how the scientific community should communicate uncertainty about interstellar human spaceflight. There is a tendency in both optimistic and pessimistic framings to treat the barriers to leaving the solar system as a unified challenge that will either be solved comprehensively or remain unsolvable permanently. Neither framing is accurate. The barriers are specific and different from each other. Some are already being worked on productively. Others require research investments that have not yet been made. A few may require conceptual breakthroughs that cannot be scheduled. Communicating this accurately matters for research funding, for public understanding, and for the long-term planning of any civilization that takes interstellar travel seriously as a future goal. Oversimplifying the barriers either direction, dismissing them as merely engineering problems that money will solve, or treating them as permanent impossibilities that should be abandoned, produces a distorted picture that does not serve anyone planning actual research or missions. The most honest summary is that leaving the solar system with a human crew is currently far beyond achievable capability, that some of the barriers are clearly solvable in principle, that others are at the frontier of known physics and require new understanding, and that the universe does not owe us a solution. The search is real, the problem is specific, and the timeline is genuinely unknown. The current state of human planning for leaving the solar system reflects this category structure. The most developed and most funded proposal for reaching another star is the Breakthrough Starshot initiative, announced in 2016 and backed by substantial private investment. The concept is to launch gram-scale probes, centimeter-sized spacecraft, not carrying biology, on laser sails accelerated by ground-based laser arrays to approximately 20% of the speed of light. At that speed, the transit to Alpha Centauri would take approximately 20 years. The probes would fly through and take brief observations, then transmit data back during the flyby. Breakthrough Starshot is instructive in the context of this script. The reason the architecture uses gram-scale probes rather than crewed spacecraft is not cost, it is survival. A gram-scale probe traveling at 20% of the speed of light will accumulate radiation damage from the interstellar medium and from galactic cosmic rays over the 20-year transit. The damage will be significant. For a machine of that size and mass, the damage is acceptable. The probe may not function perfectly on arrival, but the mission concept accounts for this. For a biological crew, the same radiation environment over the same transit time would be lethal. Breakthrough Starshot does not solve the biological radiation problem. It removes biology from the equation. This is the honest statement of where the field currently stands. The most realistic near-term interstellar mission proposal solves the crew radiation problem by eliminating the crew. Beyond Breakthrough Starshot, there are research organizations, the Initiative for Interstellar Studies, the Tau Zero Foundation, that study longer horizon mission concepts. These groups produce serious technical work. They are not proposing missions for the next decade. They are mapping the problem space, identifying the barriers, and developing frameworks for future research. The work is genuine and valuable, but none of it has converged on a crude interstellar mission plan with a realistic architecture and a launch timeline. NASA has produced mission studies for probes reaching 1,000 astronomical units, roughly 8 times the distance Voyager has traveled in under 50 years. These are serious engineering studies. 1,000 astronomical units is still well inside the heliosphere's outer regions, not interstellar space, by the definition of the heliopause crossing. They are important for planetary science and for measuring the heliospheric boundary from new vantage points. They are not interstellar missions. The pattern across all of these efforts is consistent. The missions that are technically realistic remove biology. The missions that include biology are not technically realistic. The gap between these two categories is not a gap that incremental engineering advancement is currently closing. The Breakthrough Starshot architecture, while not solving the crewed mission problem, has produced useful engineering research that informs the broader challenge. The laser sail concept requires developing very high-power, phase-coherent laser arrays capable of delivering sustained power to a rapidly receding target. The pointing accuracy required, keeping a laser focused on a centimeter-scale target moving at 20% of light speed, requires adaptive optics and control systems that do not currently exist at the scale needed. The sail material must be highly reflective, extremely thin, and capable of surviving the intense laser irradiation without ablating or deforming. The miniaturized electronics aboard the probe must survive relativistic particle bombardment during the multi-decade transit. Each of these engineering challenges is real and substantial. Some have proposed solutions, others remain open. But the research into these problems is producing knowledge that generalizes beyond the specific Starshot architecture. High-power phased laser arrays have applications in ground-based astronomy and defense. Ultra-thin, highly reflective sail materials have applications in solar sailing more broadly. Radiation-hardened electronics for relativistic environments inform the design of any deep space instrument. What Breakthrough Starshot has not produced, and what its architecture explicitly does not attempt, is a solution to the biological radiation problem. The gram-scale probe avoids the problem by having no biology, the fundamental insight that the radiation environment outside the heliosphere at relativistic speeds is incompatible with biological organisms using current protection technologies is not challenged by the Starshot architecture. It is acknowledged by it. The architecture is designed around that constraint rather than against it. This is arguably the honest starting point for any near-term interstellar program, not solving the human interstellar travel problem, but solving the probe interstellar travel problem first, learning from those missions and developing the knowledge base from which a future human program might eventually grow. There is a counterintuitive aspect to the breakthrough starshot architecture worth acknowledging directly. The proposal to send gram-scale probes at 20% of light speed is, in some ways, more ambitious in terms of the engineering required per gram of payload than any crewed mission proposal. The power density of the laser array required to push a gram-scale sail to 20% of light speed is enormous. The pointing accuracy needed to maintain illumination across the acceleration distance is unprecedented. The miniaturization of electronics and sensors into a package that fits on a centimeter-scale probe is at the extreme edge of current technology, and yet the proposal is considered more credible than crewed interstellar proposals, not because it is easier, but because it removes the most intractable barrier. By eliminating biology, it eliminates the requirement for radiation shielding, life support, biological adaptation, and crew survival across decades of galactic cosmic ray exposure. The hardest problems, the ones that may require new physics, are simply not present in the architecture. This is a meaningful signal about where the real barrier to human interstellar travel lies. It is not in the speed, it is not in the communication, it is in the biology. The physics of sending small machines to other stars is, while enormously challenging, within the realm of what existing physical principles could support with sufficient engineering development. The physics of sending biological organisms, of keeping human bodies alive and functional in the radiation environment outside the heliosphere for the decades an interstellar mission requires, is the problem that currently has no path forward. The dangerous conditions outside the heliosphere are not anomalies in an otherwise hospitable universe. They are the normal conditions of the galaxy. Most of interstellar space has no heliosphere. Stars produce stellar winds, and those stellar winds create heliosphere-like bubbles around their own planetary systems, if they have them. But between stellar systems, the default conditions are those that Voyager measured. High galactic cosmic ray flux, no magnetic protection, the interstellar medium at whatever density it happens to have. These are not extreme conditions confined to some particularly violent region. They are the background state of the Milky Way. For most of cosmic history, there was no shielded environment at all. Stars formed and burned and exploded, seeding the interstellar medium with heavy elements and accelerating particles through supernova shockwaves. Planetary systems formed around some stars, and around some of those stars, the stellar wind inflated protective bubbles. These bubbles are transient features of the galaxy, maintained only for the lifetime of the star that generates them, in a small fraction of the galactic volume at any given time. The fact that life on Earth developed inside one of these bubbles is not a coincidence in the sense of being surprising, if you think about it carefully. Life as we know it requires stable chemistry, requires DNA-based replication, requires structures that can maintain themselves against entropy over millions of generations. The mutation rate imposed by the full galactic cosmic ray spectrum, the Hz ions arriving continuously from every direction, would substantially elevate the rate of DNA damage in any organism exposed to it over geological timescales. Whether complex multicellular life with sophisticated DNA repair chemistry and the slow evolutionary development of nervous systems and intelligence could have developed in that environment is genuinely uncertain. Some scientists have raised the question of whether a heliospheric shield may be a necessary condition for the development of complex life around a star like the Sun. Not a sufficient condition, but a necessary one. The heliosphere did not just protect the solar system. It may have protected the possibility of the kind of life that produces the kind of species that builds the kind of telescopes that discovered the heliosphere. There is something specific in that circular dependency that is worth sitting with. Life on Earth evolved inside a bubble that was being continuously maintained by the same star that warmed the planet. The Sun was simultaneously the heat source and the shield generator. Remove either function and life, as we know it does not develop. Both were required. Both operated together for 4.5 billion years, while chemistry became biology and biology became complexity. Outside the bubble, the conditions that prevailed for most of cosmic history continue to prevail. The galaxy did not pause its violence to make room for life. It continued producing supernovae, accelerating particles filling interstellar space with the radiation background that the heliosphere spends its energy deflecting. The solar system is a quiet island in the much noisier sea. The question of whether the heliosphere is a necessary condition for complex life connects to a broader discussion in astrobiology called the rare Earth hypothesis. In 2000, paleontologist Peter Ward and astronomer Joe Kirschvink published an argument that complex animal life on Earth might be the result of an unusually large number of coinciding favourable conditions, not just liquid water and a suitable temperature, but a large moon to stabilise Earth's axial tilt, a giant outer planet like Jupiter to clear the inner solar system of large impactors, a specific galactic location in a relatively quiet region between spiral arms, and a star with the right kind of steady-state stellar wind to maintain a protective heliosphere. Each of these conditions is plausible individually. The argument is that the combination of all of them simultaneously is statistically improbable enough that complex animal life might be rare in the galaxy. The heliosphere's role in this argument is specific. A star with a weaker or more variable stellar wind would produce a smaller, less stable heliospheric bubble. A star with a much stronger wind might produce a bubble that protects too aggressively, deflecting not just galactic cosmic rays, but also cosmic ray secondaries that may play a role in cloud formation and climate. A star without a consistent enough stellar wind to maintain a stable heliosphere would expose its inner planets to galactic cosmic ray flux that fluctuates dramatically with the star's activity cycle. The Sun's solar wind has been relatively steady and consistent for the roughly 4 billion years that life has been developing on Earth. This consistency allowed the heliosphere to provide stable, predictable shielding while life's chemistry became gradually more sophisticated. Whether this steadiness is typical of the class of stars most likely to host habitable planets, or whether it is itself a somewhat unusual property, is an active area of stellar astrophysics research. The question is not settled. The heliosphere's role as a specific precondition for complex life is a hypothesis, not a confirmed finding. But the measurement from Voyager, the step function at the heliopause, gives the hypothesis a concrete physical foundation that it lacked before 2012. There is one more layer of the problem that has not yet been named. Everything discussed so far concerns the outward leg, crossing the heliopause, surviving the galactic cosmic ray environment, navigating the interstellar medium at speed, transiting the Oort cloud region. Each of these problems compounds the others. Together, they constitute the barrier to leaving. But any mission that intends to return, any crewed mission that expects the crew to come back, faces every barrier twice. On the outward trip, and again on the way home, there is a fundamental law in rocketry called the Tsiolkovsky rocket equation. It describes the relationship between the mass of propellant a spacecraft must carry and the velocity change it needs to achieve. The relationship is not linear, it is exponential. For every unit of velocity change required, the propellant mass needed grows exponentially. Double the velocity change, and the required propellant mass does not double. It can increase by factors of 10 or 100 depending on the exhaust velocity of the propulsion system. A round trip to another star requires the spacecraft to accelerate to interstellar speeds, then decelerate at the destination, then accelerate again for the return, then decelerate again at Earth. 4 large velocity changes, each one requiring propellant mass that must have been carried since departure. The total propellant mass required for a round trip at even 10% of the speed of light, using any conventional or nuclear propulsion concept, exceeds anything that has ever been contemplated for a launch vehicle. The numbers are not slightly larger than current capability, they are orders of magnitude larger. Laser sail concepts, like breakthrough Starshot's architecture, avoid some of this by using an external energy source, the ground-based laser array, for acceleration. But a laser sail that is accelerated away from Earth by a laser array cannot be decelerated at the destination by the same array. A return trip requires either a laser array at the destination, which does not exist, or an entirely different deceleration mechanism, which also does not exist. On the return leg, every radiation barrier is traversed again. The galactic cosmic ray exposure accumulates on the homeward leg as it did on the outward one. The interstellar medium at speed presents the same forward particle flux. The crew's biological deterioration, which has been progressing since departure, continues through the return. The mission duration, already measured in decades at minimum, approximately doubles for a round trip. The return problem is not a new kind of barrier. It is all the existing barriers applied twice to a crew that has already been exposed to them once. It does not make leaving the solar system twice as hard. It makes it substantially more than twice as hard because the propellant mass requirement grows exponentially and the biological accumulation is roughly additive. The challenge of the return trip is also a challenge for the design of any propulsion system because deceleration requires the same energy as acceleration. At the speeds relevant to interstellar travel, the majority of the mission's energy budget is consumed in changing velocity, accelerating at departure, decelerating at arrival, accelerating again for the return, and decelerating again at Earth. Each of these velocity changes requires either burning propellant or exchanging momentum with something external. Propellant-based systems face the rocket equation in its most extreme form. The propellant itself has mass, and that mass must be accelerated along with the payload. The heavier the propellant load, the more propellant is needed to accelerate it, in a compounding relationship that grows exponentially with the required velocity change. For a round trip at 10% of light speed, using a realistic rocket exhaust velocity, the ratio of initial propellant mass to final payload mass is not 10:1 or even 100:1. It is astronomical in the literal sense of the word. Laser sail concepts solve the acceleration phase by using an external energy source. The laser array accelerates the sail without the sail needing to carry its own fuel. But this only works while the spacecraft is within range of the laser array. Deceleration at the destination and acceleration for the return require either a laser array at the destination, which does not exist, or some other mechanism. Proposed alternatives include magnetic braking, in which the spacecraft deploys a magnetic field that interacts with the interstellar medium to produce drag, solar sail braking using the radiation pressure of the destination star, or gravitational assist from the destination system. Each of these has serious limitations. Magnetic braking requires mowing the density and properties of the interstellar medium along the route, produces enormous forward radiation flux at high speeds, and generates the interstellar medium particle beam problem in its deceleration phase rather than its acceleration phase. Solar sail braking requires deploying a sail structure on approach, complex, vulnerable, and only useful if the approach geometry is right. Gravitational assists require multiple precise flyby maneuvers at the destination system, extending the mission significantly. None of these alternative mechanisms have been demonstrated at any scale relevant to an interstellar mission. The deceleration problem is, if anything, harder than the acceleration problem. Set all of this together and ask the direct question: what would a survivable human interstellar mission actually require? Not what current technology provides, what the physical problem demands. It would require a radiation shield against the full galactic cosmic ray spectrum that does not produce a worse secondary cascade in the highest energy particle range. No such shield currently exists. The requirement is not for a better material, it is for a solution that does not yet have a clear physical principle behind it. It would require an active deflection system capable of redirecting Hz ions omnidirectionally from a spacecraft-scale platform, while also addressing the neutral particle components, neutrons, that magnetic fields do not deflect. The engineering requirements for such a system, in terms of mass and power, have not been met. No deployment timeline for this technology exists. It would require a propulsion architecture that achieves high enough speed for a human lifetime transit while remaining slow enough to avoid the lethal interstellar medium effects at higher fractions of light speed. This window may exist. Whether it can be threaded with a propulsion system compatible with launchable mass budgets is not currently known. It would require a biological adaptation to Hz ion damage patterns that exceeds what natural DNA repair mechanisms provide, potentially through pharmaceutical intervention, genetic modification, or approaches not yet developed. Sustained across decades of exposure to a radiation environment human biology was never calibrated against, it would require complete internal capability for every conceivable emergency, medical, mechanical, navigational, biological, for the entire mission duration, with no external support and no resupply. Every contingency must be anticipated and carried. Every expertise must be on board. Every spare part must be packed. Each of these requirements can be stated precisely because each corresponds to a specific barrier identified by research and measurement. The requirements list is not speculative. It is derived from what the known physics says the problem demands. Some items on it are reachable with engineering development. Others require fundamental physics that does not currently exist. None of them are trivially solvable with more time and funding. The requirements for a survivable human interstellar mission can be expressed in terms of specific physical thresholds, which makes the gap between current capability and what is needed concrete rather than vague. For radiation protection, the requirement is to reduce the total annual galactic cosmic ray dose to the crew to below the career limit of approximately 1 sievert for the highest risk particle types, including Z-ions, over a multi-decade mission. Current ISS shielding provides roughly half the protection needed even in low Earth orbit during solar maximum. Outside the heliosphere, the unshielded galactic cosmic ray flux is roughly 3 to 10 times higher than what astronauts receive on the ISS. Achieving the target dose for a 20-year mission outside the heliosphere requires a reduction in the effective dose rate of approximately 2 to 3 orders of magnitude compared to unshielded exposure. No current or projected passive shielding achieves this without the secondary cascade problem exceeding the benefit. For the interstellar medium at speed, the requirement is to reduce the forward particle flux at the operational speed to below the acute radiation threshold. At 10% of light speed, this may be achievable with modest frontal shielding. At 20%, it likely is not with any passive shield design. The operational speed must therefore either remain below the threshold where the interstellar medium dominates, or the shield must solve a physics problem that has not been solved. For propulsion, the requirement is to achieve a velocity that completes the mission within a human generation, roughly 50 to 80 years at maximum, while staying below the speed at which the interstellar medium becomes acutely lethal. If the lethal threshold is around 15 to 20% of light speed, and 50 years at 15% of light speed only covers about 5 light-years, barely reaching Alpha Centauri with no margin, the mission architecture is extremely tight. Adding deceleration requirements extends the mission further or demands higher peak speed with all its attendant problems. Each requirement is derivable from known physics. Each is currently far from achievable. The gap is not uniform, and that matters for how a research agenda should be structured. The requirements list also points towards something worth stating clearly. The gap between current capability and what is needed is not primarily a gap in engineering talent, resources, or ambition. It is a gap in physical understanding. The secondary cascade problem, the neutron shielding problem, the interstellar medium at speed problem. These are not problems that would be solved if NASA had a larger budget, or if private companies invested more heavily in spacecraft shielding. They are problems that would be solved if the underlying physics were better understood and if that understanding suggested a new approach that does not currently exist. This is a different kind of problem from the ones that space programs typically face. Most space program challenges are engineering challenges in the sense of figuring out how to implement known physical principles in reliable, mass-efficient, cost-effective systems. The challenge of radiation protection for human interstellar travel is, at its core, a physics challenge, one that requires either discovering a new physical principle or applying known principles in a way that has not yet been identified. This does not mean the problem is unsolvable. Physics has surprised us before. The laser, the transistor, superconductivity at high temperatures, the discovery of gravitational waves, all of these were the products of physical understanding that did not exist until it did. There is no reason to assume that the physics relevant to interstellar travel protection has been fully catalogued by current science. But it does mean that the path to human interstellar travel runs through basic physics research as much as through engineering, and that this distinction should shape how the problem is approached. Come back to the beginning. In August of 2012, a small machine crossed a boundary 11 billion miles from the planet where it was built. The cosmic ray subsystem registered a step function in the data. Inside, one level; outside, another. The change happened at a line, and the line was real. That data is still being transmitted. Voyager 1 is still out there, still sending a signal that takes nearly 24 hours to arrive, still moving through a part of the galaxy that no human-built object had reached before, and no other human-built object had reached since. It is in the environment that this script has spent the last hour describing: full galactic cosmic ray flux, the interstellar medium at its ambient density, the default conditions of the galaxy, unfiltered. The heliosphere is not the edge of the solar system in the way a fence is the edge of a yard. It is an active structure powered by a star, maintained continuously by the star's energy output, spanning more than 100 astronomical units of space around the solar system. Crossing it means entering a physically different environment. Not a larger version of the inner solar system, not a continuation of the same conditions at greater distance, but a qualitatively different physical medium, with different radiation characteristics, different particle populations, and none of the magnetic infrastructure the Sun has been maintaining around this region of space for 4.5 billion years. Life on Earth has never been outside this structure. Every organism that has ever existed on this planet evolved inside the heliosphere, inside Earth's own magnetic field, under an atmosphere that provides additional filtration. These protections were not designed. They were not engineered. They were present before life existed, and life developed inside them, and the biology that exists on Earth reflects, at the molecular level, those conditions. The DNA repair mechanisms, the cellular tolerances, the radiation sensitivities of every organism that has ever lived, all of it was calibrated against conditions inside the shield. Leaving the shield means leaving the environment in which life was built. The danger is not external to the traveler. It is a mismatch between what the traveler is and what the destination requires. This is what the data from Voyager showed. This is what the secondary cascade problem in passive shielding reveals. This is what the relativistic interstellar medium calculation describes. And this is what the biological deterioration studies demonstrate at the small scale available to us in low Earth orbit. The solar system is a lifeboat, not metaphorically, physically. The heliosphere is what makes it a lifeboat. The active, maintained, star-powered magnetic bubble that reduces the galactic radiation background to levels where 4 billion years of evolving chemistry could produce biology complex enough to ask this question. The title asked why leaving is far more dangerous than you think. The answer is not that leaving is dangerous in the way deep space is always dangerous. Cold, empty, remote. The answer is that leaving the heliosphere is a departure from the only physical environment in which biology as we know it was built to survive. The dangers outside it are not bigger versions of the dangers inside it. They are different in kind. They do not get better with thicker walls. And the structure that's been protecting this region of the solar system for 4 billion years is powered by the Sun, not by anything a spacecraft could carry. A step function in a data graph from a 35-year-old machine, 11 billion miles away, told us this clearly, precisely, and permanently in August of 2012. The line is real. The measurement that started this script was not particularly dramatic to observe. A graph. A line that rose sharply at one point. Data from an instrument that had been running continuously for 35 years, recording readings that changed in August 2012 in a way that told careful analysts something about where the spacecraft was and what had changed around it. It was not a spectacular event in the way a launch or landing is spectacular. There was no countdown, no visible moment of crossing, just numbers arriving at JPL transmitted at the speed of light across more than 17 hours of distance, describing what an instrument on a small machine was measuring as it moved through a region of space that no human-built object had entered before. But the data said something important. It said that the boundary between the heliosphere and interstellar space is real and measurable. It said that the radiation environment changes significantly at that boundary. It said that the protective influence of the Sun, the magnetic bubble it inflates around the solar system through its continuous outflow of charged particles, extends to a specific distance and no further. Beyond that distance, the galaxy is present in its full, unmediated character. This script has described what that character is: the radiation from violent stellar deaths throughout the Milky Way, arriving continuously from all directions at significant fractions of light speed. The shielding paradox that makes the intuitive engineering solution partially counterproductive. The speed trap that transforms the neared vacuum of interstellar space into a particle beam for any spacecraft moving fast enough for the mission to be useful. the Oort cloud that extends the solar system's potential collision hazard far beyond the heliopause. The biology calibrated against conditions inside the shield. The isolation that removes every external mitigation from every risk simultaneously. None of this was invented. All of it is either directly measured, the Voyager crossing data, the ISS physiological data, the secondary cascade physics documented in decades of particle physics research, or derived from physical principles that are well understood. The heliosphere's protective function has been measured from inside and outside. The scale gap between it and any spacecraft scale shield is a consequence of the physics of magnetic deflection. The interstellar medium calculation follows from relativistic mechanics. The biological limits follow from radiation biology and from the data on what microgravity does to the human body across extended missions. The solar system is a lifeboat, not because nothing dangerous exists inside it. Solar flares, asteroid impacts, and the long-term evolution of the Sun all present hazards, but because the heliosphere reduces the default radiation environment of the galaxy to levels where complex DNA-based biology could develop over 4 billion years, and where that biology can now sustain itself. The heliosphere is the fence around the island. The island is habitable because the fence is there. Leaving it requires solving problems that, taken together, currently exceed the limits of what physics and engineering have achieved. Some of those problems will yield to sustained effort. Others may require new physics. All of them are specific, measurable, and now understood well enough to know what a genuine solution would need to provide. That is not the end of the story. It is the correct beginning of one. Good night.